In an era marked by evolving security threats, safeguarding lives and infrastructure demands cutting-edge technology. Explosive trace detection, or ETD, has emerged as a critical component of this defense, playing a vital role in detecting and deterring the use of explosives. ETD focuses on identifying minute traces of explosive materials, often invisible to the naked eye. These traces can linger on surfaces, clothing, and luggage, making their detection crucial for preventing catastrophic events. Early ETD methods were relatively rudimentary, relying on colorimetric tests and gas chromatography. Today, ETD encompasses a sophisticated array of technologies, each leveraging advanced scientific principles to detect and identify even the smallest traces of explosives. From safeguarding our skies to protecting our communities, ETD stands as a critical line of defense against the ever-present threat of explosives. At the heart of every ETD system lies a fundamental principle. Explosives, even in minuscule quantities, emit distinct chemical signatures. These signatures, often composed of volatile organic compounds, or VOCs, serve as telltale signs of their presence. ETD technologies are designed to detect and analyze these VOCs, providing a means to identify the presence of explosive materials. One of the key scientific principles behind ETD is the concept of vapor pressure. Explosive materials, like many other substances, have a tendency to release small amounts of vapor into the surrounding environment. ETD systems are engineered to detect these incredibly minute concentrations of explosive vapors. Another crucial aspect of ETD lies in the unique chemical properties of explosives. Many explosives contain nitrogen-based compounds, such as nitrates, nitrogroups, and amines. By combining high sensitivity with high selectivity, ETD technologies provide a reliable means to identify the presence of explosives, even amidst a complex chemical background. Over the decades, ETD technology has advanced significantly, resulting in a diverse array of detection methods. Ion Mobility Spectrometry, or IMS, is widely used in airport security. It separates and identifies ions based on their mobility in an electric field. Chemiluminescence relies on light emission from a chemical reaction. Mass Spectrometry identifies components based on their mass-to-charge ratio. Canines remain an integral part of ETD. The process of explosive trace detection begins with the collection of a sample. The most common sampling technique involves swabbing surfaces that may have come into contact with explosives. Trained security personnel use sterile swabs, typically made of cotton or microfiber, to collect trace particles from various surfaces. These surfaces can include luggage exteriors and interiors, electronic devices, clothing, and even hands. Once the swabbing is complete, the swab is carefully placed into a specialized container designed to preserve the integrity of the sample. The sample is then transported to the ETD instrument for analysis. Upon arrival at the ETD instrument, the swab is inserted into a heating chamber or subjected to a process called thermal desorption. The goal is to minimize the time taken for detection while maintaining the highest levels of accuracy and reliability. While swabbing remains a widely used sampling technique in explosive trace detection, advancements in technology have led to the development of non-contact detection methods. These methods offer several advantages, including faster screening times, reduced risk of contamination, and the ability to detect explosives at a distance. One such non-contact method is walk-through explosive trace detection, or WTETD. As individuals walk through the WTETD portal, puffs of air are directed towards their clothing and belongings. These air currents dislodge any trace particles of explosives, which are then drawn into the detection unit for analysis. Another non-contact method utilizes specialized lasers to detect explosives from a distance. Non-contact ETD methods are particularly valuable in situations where speed and efficiency are paramount. When an ETD system detects explosive traces, it triggers an alarm, indicating a potential security threat. Not all alarms are created equal. ETD systems provide different levels of alarm based on the type and concentration of explosives. Most employ a multi-tiered alarm system. A low-level alarm, indicated by a yellow light or single beep, suggests trace amounts of explosives. A high-level alarm, with a red light or continuous sound, suggests significant detection. Despite significant advancements in ETD technology, canine detection remains an indispensable tool in the fight against explosive threats. Dogs possess an unparalleled sense of smell, capable of detecting odors at concentrations far below the threshold of even the most sophisticated ETD instruments. This remarkable olfactory ability, combined with their trainability and agility, makes canines invaluable partners in explosive detection. Explosive detection canines undergo rigorous training regimens to hone their ability to detect a wide range of explosive materials. The role of canines in ETD extends beyond simply detecting explosives. Their mobility and ability to navigate complex environments make them ideal for searching large areas, such as aircraft cabins, cargo holds, and crowded public spaces. The partnership between human handlers and their canine counterparts represents a powerful synergy, combining cutting-edge technology with the irreplaceable instincts of these highly trained animals. The field of explosive trace detection is in a constant state of evolution, with ongoing research and development efforts focused on enhancing the sensitivity, speed, and accuracy of detection methods. One promising area of research is the development of nanotechnology-based ETD sensors. These sensors utilize nanomaterials such as carbon nanotubes and graphene, which possess unique electrical and chemical properties that make them highly sensitive to the presence of explosive molecules. Another area of focus is the development of standoff ETD technologies, which allow for the detection of explosives from a safe distance. These technologies utilize lasers, terahertz radiation, or other forms of electromagnetic radiation to detect the unique spectral signatures of explosives. Artificial intelligence and machine learning are also playing an increasingly important role in ETD. AI algorithms can be trained on vast datasets of explosive signatures, enabling them to identify patterns and anomalies that may indicate the presence of explosives. While ETD technology has made significant strides in recent years, it is not without its limitations and challenges. One of the primary challenges in ETD is the issue of false positives. As mentioned earlier, ETD systems can sometimes trigger alarms due to the presence of substances that share similar chemical signatures with explosives, such as certain cleaning products, perfumes, or even some types of food. False positives can lead to delays, inconvenience, and unnecessary security procedures. Another challenge is the detection of homemade explosives, HMEs. Unlike commercially manufactured explosives, which tend to have consistent chemical compositions, HMEs can be concocted from a wide variety of readily available ingredients. The portability and ease of use of ETD equipment also present ongoing challenges. There is a constant need to develop more compact, user-friendly, and cost-effective ETD systems that can be readily deployed in a variety of settings. The future of explosive trace detection is brimming with possibilities, driven by the relentless pursuit of enhanced security measures and the constant evolution of threats. Researchers and engineers are exploring a multitude of avenues to push the boundaries of ETD technology, focusing on key areas such as miniaturization, enhanced sensitivity, and real-time detection capabilities. One prominent trend is the development of microfluidic ETD systems. These systems utilize miniaturized channels and chambers to manipulate tiny volumes of liquids, enabling the creation of highly compact and portable ETD devices. Another promising research avenue involves the integration of artificial intelligence and machine learning into ETD systems. AI algorithms can analyze vast amounts of data from various sensors and sources, enabling the identification of subtle patterns and anomalies that may indicate the presence of explosives. Furthermore, researchers are exploring the use of bio-inspired ETD sensors, drawing inspiration from the highly sensitive olfactory systems of animals like dogs. As technology continues to advance, the future of explosive trace detection holds immense promise.